Good morning and welcome to a terrific Tuesday once again. Thank you very much for gathering your Desmos app and getting that fired up on your laptop or iPad or the device that you have available. We are going to be doing some investigations in Desmos today, and that's going to follow the following format. So here is the handout. I'm going to give you a tour of the handout and the things you're going to be looking at, and then you're going to be investigating these things yourself. So here you have what's the heck is going on here? Y is equal to A, F, K, X minus D plus C, lots of brackets. All right, let's talk about what we're looking at here. The numbers that are bolded, and I say numbers, and they're actually letters, and I hope you're used to that at this point, that letters are numbers too. They're just numbers we don't know yet. They're just numbers that could be some value. Okay? A, K, D, and C are the bolded numbers here, and these are the four numbers that when we change them will transform functions. So when we're looking at the first one here, A, we'd have some function that's y is equal to A multiplied by the output of functions. So A is a number that multiplies the output of functions. When you look, and go ahead and flip the page with me, here is the number K. Oh, so do you need a handout? No. Here, I'll grab you one. So K is the number that grab some for your compatriots as they go back. So you need one of these. So K is the number that, and Alina needs one too. K, you'll see on page 2, is now inside the bracket here, multiplying the input of a function. So K is a number that's going to multiply inputs. A is a number that multiplies outputs. And you're going to be investigating the different roles that these numbers play, following along the different instructions. Now, what about C and D? Well, here's D. D is a number that we're subtracting from inputs. So as we're looking at these functions, you're going to subtract those from inputs. And then over here, C. C is a number that we are adding to outputs. So those are our four different numbers that we're using here. A multiplies the output of a function. So notice that here is my function, f of x. And it's hiding in there in between all of these four numbers. A multiplies the output. K multiplies the input. D is being subtracted from the input, and C is being added to the output. So that's the nature of these four numbers. And we're going to take a few days to investigate all four numbers and what they're doing. A, K, C, and D. So how are we going to do that? Well, you follow the instructions. Here in the first one, it says graph the parent function y is equal to x squared. So we're going to follow along with me. You're going to do this one together. We're going to graph y is equal to x squared. And then we see our nice predictable parabola. This is called the parent function. The parent function of all quadratic functions. So in Unit 1, we were factoring these. We were writing them in standard form. We were writing them in vertex form. We were writing them in factored form. Okay. This one, x squared, is the progenitor, the ancestor of all of those different functions. So we call it the parent function. By transforming x squared, we can get all the other quadratics. And we can get that by changing A, K, D, and C. So the next instruction says graph it. So you're going to go ahead and graph it here. And I suggest practicing beautiful graphs. Now, I don't mark you on how beautiful they are, but a beautiful graph does help you estimate better. Some of you during the golf ball question on the test, because you're good at drawing beautiful parabolas, your graph was a very good guess, even those of you who couldn't do the algebra correctly. So I know that it has this point 0, 0, the points 1, 1, the point 2, 4, the point 3, 9. I can get that from Desmos. I can check this in Desmos. It's symmetrical, so it has these points as well. I put on the integer points, and then I'm going to link that with a beautiful curve. Just like so. The last thing to add, arrows showing that this keeps on going to infinity in those directions and beyond. So now we've sketched it on the following coordinate plane. We are going to be graphing more parabolas after we do some transformations here, And it would be nice if you use some different colors for those. It will make your work pop a little more and might add to your learning. So if you have some extra colors, use those. If not, I have some in my bucket up here. You can borrow some of my pens. So in line 2, graph y is equal to ax squared and add a slider for a. So let's take a look at how we do that. You're going to go here, push enter, and say y is equal to ax squared. And it says add a slider. Well, yes, please. I served sliders at my wedding because I'm a cheapskate. No, it's not true. It's because it was a fun way to have wedding food when we had sliders. Sliders are also great here on Desmos. Now, what I've graphed here, you'll notice if I toggle that on and off, it's the same thing as that y equals x right now because a is equal to 1. What the slider allows you to do is investigate what happens when I change a. What happens if a becomes, say, 1/2? There it is, 1/2. There's a is 1/2. Oh, look, it's got flatter. And then I say, well, what happens if a is bigger? Oh, it got bigger. Okay, so there, it's much higher now. So, and then I want to think, well, what is that doing? Well, this is a. It's a number that's multiplying the output of this function. It's taking whatever x squared outputs and multiplies that. So it's raising all the outputs of the function. All of the y values are getting bigger. If a is negative, it seems to do something. It changes. So if I say a is -1, how would you describe that? What have I done to this parent function with this transform function? What did I do there? Is that resting question hand, or do you know, Julia? No. What happened to this this parabola here? It changed its direction. Did you say? Yeah. So it now opens downwards, and if I had to describe what happened, it looks like it's a mirror image of the other parabola. If I said that this parabola is a mirror image of that one, where's the mirror? The x-axis is the mirror. Very good. So negative values of a reflect these functions in the x-axis. It transforms the x-axis into a mirror. It's pretty cool. So that's what we did there when we said a is -1. And now let's go back to our handouts, and we'll keep going. Use the slider, investigate the following functions on the table on the back of the page, and compare to this parent function. Okay, so flip over. Take a look at the table. So y is equal to 2x. Okay, so y is equal to 2x. Oh, where am I? I'm up here. There we go. This is the first one we've been asked to investigate. So let's go over there and take a look at it. So set your a to 2. And now you have y is equal to 2x squared. Here is the blue one. All right, it's new. So we're going to go ahead and we're going to look at that, find some points. Like here's the point 1, 2. Here is the point, what else can I find? Here's the point 2, 8. Okay, so find some of your integer points on here. Here's the point -2, 8. Okay, find some of your integer points and plot them. So you're going to go back over here and you're going to say, okay, I've graphed this. Let's go ahead and put it on there. Thank you very much. That's very kind of you all. And let's plot some of those points. I'm going to do it in a different color. I'm going to do that in orange. So here, I said I found the point 1, 2 and the point 2, 8. So I put those on. I also have symmetrical points on the other side. So there's a point 2, 8. And then I join these with a beautiful curve. And it's going to start looking a little bit like someone went crazy with a spirograph. Like it's going to be this like weird mathematical art as I graph more of these here. So there's, and I could label this. This is y is equal to 2x squared. And this one I could label as y is equal to x squared. And because I'm using different colors, it's easy to see what's happening. Now I can go back to this page and say, well, what happened there? Let's compare that to the parent function. So how would you describe the change from the red parent function? This is the original x squared, the OG quadratic, and then its child here, 2x squared. What changed? What happened? What did we do to that to make the red one become the blue one? Yeah, and what did the graph do? It kind of looks like it's thinner, doesn't it? Yeah, and it is. Does it still go to infinity in both directions of x? Yeah, it still does. We can still have negative infinity for x and positive infinity for x. Well, not infinity, but approaching that. Yeah, so it still goes out really wide. But if we take a look at some of the points here, like x is equal to 1, okay? So here's the line x is equal to 1. This point here at 1, 1 now corresponds to this point at 1, 2. Why do you think that happened? That this point 1, 1 got pulled up there to 1, 2?
Because the A value is 2.
Because the A value is 2. So now all of the outputs have been multiplied by 2. So if we had to describe this as a vertical stretching, we would say that all of these values were stretched vertically by a factor 2. So let's go ahead and put that down over here. Comparison to parent function. So I would say, these are things I've heard. It got thinner. The y values doubled. And the my favorite, the graph was stretched. By factor 2 in the vertical direction. It's like it got twice as tall, and it grew bigger. Okay, it's like it's a little weird because the red one is the parent function, but the blue one is taller. It's like the red one is the 8-year-old version, and the blue one is fully grown. It just got taller. Everything got bigger by factor 2. Okay. If we also drew a line out here at x is equal to 2, we would notice that this point here at 2, 4 became the point 2, 8. Okay? Vertical stretch by factor 2. Now, let's take a look. What else are we investigating? Now we look at 3x. What do you predict will happen when we go to 3x? Aiden?
It'll get stretched thinner.
Yeah, it'll look thinner, okay? Now,
factor 3.
Another thing by factor 3. It'll be stretched vertically by factor 3. It'll be thinner again. Okay, so what I want to point out is it got thinner is still correct. Y values doubled. That's also useful to point out. Write down all the things you notice here. This is for your qualitative and quantitative observations. If it reminds you of the smile of a character from a cartoon you watch, write that down. Okay? It's like whatever you observe, write down. That's the purpose of this exercise. Okay? But you want to also be working towards these kinds of realizations. When I put this 2 in here, it got stretched by factor 2. This would be factor 3. So let's go take a quick look, and then we'll look at y equals negative x and y equals 0.5. Okay? So we're going to take a look at those two next. So here is a is equal to 3. So there, now it's stretched even more. So this point 2,4 became the point 212. So there's a point 212. And here's a point 2,4. So now it's been stretched by a factor 3 vertically. It got thinner still. It's now even more thinner. It's narrower. There's lots of different ways to describe this transformation. The really useful one to notice is that it's been stretched by factor 3. So we expect to find the point 1,3 here. There's the point 1,3. There, right there. And that was based on this point 1,1 being stretched by factor 3 upwards. Okay. Now if we take a look at negative values of a, which I've already shown you, we've previewed those. Now, we want to be able to say, okay, that flipped. It became a sad parabola instead of a happy parabola. It's now no longer a bowl collecting rainwater. It's now an umbrella shielding you from rain. All are really valid observations. The really important mathematical one to be able to notice is that now the function was reflected in the x-axis. Okay? Function was reflected in the x-axis. Sorry?
You write that in the wrong way.
No, that's in the right place. Yeah. So here is a is negative 1. So y is equal to negative x squared. And if I take a look at this one here, you'll see the red one is my parent function. That's the original function there. And then the blue one is the now transformed function with an a of -1. It's like it's looking at itself in the mirror, and it loves itself so much that its nose touches its own reflection in the mirror. Camden, did I just break you?
No.
No? Okay. All right. Yeah, no, that's fine. I thought you were like, oh my goodness, Mr. Jennings. Anyway, if you imagine this as a function looking at itself, loving itself, and touching its nose in the mirror, like I've never thought of that before, but if that's what you think, then that's also a useful thing to build into your memory. It's like, oh yeah, I remember the function of a negative a value. It reflects it in the x-axis. The x-axis is like a mirror now to that function. Okay, so those are the various investigations you will make. This one, we're multiplying by a half. It takes the function and it makes it flatter, but it's still positive. Okay, and then you're going to investigate some tables of values as well. And you can draw your tables of values, and these correspond to the functions that we've looked at. You can draw your tables of values from the Desmos as well. You don't have to calculate each one independently, although it's not that hard. Here, -2 squares to 4, and 4 times 1/4 would just be 1. I mean, you can do these ones pretty quick. But let's take a look at this one here. Y is equal to 0.25 x squared. Okay, so now I'm going to make a 0.25. 0.25, there we go. So now there's my a value of 0.25. I'm now investigating the last one. And it tells me I want to know these values of x. So let's investigate them. -2, -1, 0, 1, and 2. So at -2, I can go over here. And I can find, okay, at -2, my original value is 4. Now it's 1. Why? Because a is 1/4. So all of the outputs just got shrunk by a factor 4. They have been stretched by a factor 1/4. They became 1/4 their height. So that's at this point here. So I can go ahead and write that down on my table of values. That gave me a 1. Right? And then I go over here and I say, well, let's see when x is -1. That's this point over here. Oh, and that's y value 0.25. That's y value 1/4. So you can write that down as 0.25, or you could write that down as 1/4. I think of it as 1/4. I don't know about you, but 25 cents to me, I don't say 25 cents, I say a quarter. All right, and then 0, well, 0, let's check out 0. And so you can look at Desmos and find these values. There's 0, 0, so it also goes through that point. The point 0, 0 stretches to 0, 0 for all of these quadratics. And then we would investigate x is equal to 1 and x is equal to 2. And we would find, where did that point land? Where did it go? And so there, this is point 1, this is 1/4, and this is 0. Okay, so you're going to fill in those table of values and see. Not only can you transform your graphs, you can also transform your table of values with this stretch factor a. Okay, now it's an example of how you're going to investigate the letter a. Camden, did you have a question?
What did you write for the negative one, for the negative x?
Oh, for negative x? Oh, I said the function was reflected in the x-axis. Very useful to think of this as a reflection.
Was that it, or is there more?
Oh, you could say it's now a really narcissistic parabola that gets so close to its own reflection that its nose touches the mirror. You could say that. You could say, this reminds me of a logo from my favorite brand. I don't know. You're going to share your insights there. Now, let's take a look at this one here, which is investigating k. Now, we're going to be looking also at new parent functions today. Here is the function y equals x squared. This looks like half of a parabola on its side. So let's take a look. So now I'm going to, my first instructions were to clear all my functions and then create a new function. Y is equal to, and then how do you do the square root? Well, you can bring this keyboard up here and click your that. And then put that away and carry on. So y is equal to x, the square root of x. So there it is. Notice that it looks like half of a parabola. Why don't I see any negative outputs? Why don't I see any negative values of y? Aiden?
Because you can't square root something. something to get a negative?
Yeah. The square root's always going to be the square root here, it's always a positive number. So when I take, I also have no negative values of x. So the domain and range is x and y are both positive. X and y are both greater than 0 here. Now, I am going to be using this to investigate this number k. Okay? Now, k is actually going to multiply the input. We're not multiplying the output anymore, we're multiplying the input. And it's going to do something in the horizontal dimension, similar to what was happening with a in the vertical dimension. So, first of all, we want to sketch this. And so I would find that I have the point 0, 0, and the point 1, 1, and the point 4, 2, and the point 9, 3, because it looks like a parabola that's on its side. So I start by sketching my parent function like that. I can just get that from Desmos. And then I'm not going to do the whole thing with you. I just wanted to go over these 4 values quickly first. Now we're going to investigate k. So to do that, I'm just going to take this, copy, put in another one, paste, put in here my value k. And I'm going to add a slider. So now I have a new function. And when I increase k, something strange happens. Oh, that's interesting. When I decrease k, oh, look at that. Oh, wow, what happened there? How would you describe a k of -1? How would you describe what's happening to that function there?
Reflect on the y-axis.
Now it seems like it's mirroring. Yeah, that's great. Yeah, so that's a great realization. So as you flip over, you'll notice that k is -1 is one of the things you're investigating here. And so you could write down now, and you want to get excited. You want to be like, wow, now the mirror is the y-axis. You don't have to sound like a medieval monk.
Where is that?
It's on the next page. The function, yeah, this is k is equal to -1. This is -1 is k. So the function reflected in the y-axis. Okay. So here's our parent function, which is y is equal to the square root of x. But now let's take a look at some of the other values of k. And to show you them, I'm going to put in some values of y. Y is equal to 1, and y is equal to 2. Okay. Now let's take a look when I have k values here. I'm going to start my function just with the parent function over there. So now let's take a look at these points. We have the point 1, 1 here, and the point 4, 2. Okay. Watch what happens as k, let's say k to 2. That's the next thing we're supposed to investigate. All right. Now, what's happening in the horizontal dimension to these points when a k value is equal to 2? Let's zoom in a little bit. Come up here. Here is this 1 point. 1, 1. It got pulled over there to 1/2 1. Here's the point 2, 4. Sorry, 4, 2. So I have this problem inverting points. And it got pulled to the point 2, 2. So what's happening with these functions as I increase the value of k that multiplies inputs? K and a are different. A was multiplying the output of the function. K is multiplying the input. It's multiplying the x values as I put them into the function. What is that doing as I increase k? What happened to my x values? They got cut in half. Look at that. A k of 2 cut my x values in half. Let's check a k value of 4. Let's just investigate a k value of 4 and see what's happened. Oops. So k value, k is equal to 4. Sometimes the slider is a little annoying. There we go, 4. So now let's take a look at this point. This was the point 1, 1. Now it's the point 1/4 1. This was the point 4, 2. Now it's the point 1, 2. So as I increase k, what's happening horizontally as k gets bigger? what's happening to k as I change to what's happening to the function as I change k? I'll graph them each separately. This is the point 2. This is 2x squared. This is y equals 4x squared. And now let's take a look at y equals, oops, let's just do it this way. Oops. Y equals 1/2 multiplied by x. All right. So let's investigate these different ones here. Oops. Yeah, so here is our line y is equal to 2. Let's take a look at these functions here. Here's our parent function. Has the point 4, 2 on it. When I made a k value of 2, it mapped over here to 2, 2. When I made a k value of 4, it mapped here to 1, 2. When I made a k value of 1/2, now this mapped out to 8, 2.
So
What's this value of k doing? What's it doing?
being divided by.
Doesn't it have like kind of the, like, it's working, we can see it working horizontally and pulling the function like towards the y-axis or away from the y-axis horizontally.
The lower the number, the further away it is from the y-axis.
But yet, like, small values of k were pushing it away from the y-axis. Big values of k were pulling it towards the y-axis. So it's like a stretches horizontally, but k is like increasing the gravity of the y-axis and pulling things, compressing them towards the y-axis. So when you are making your observations here, you might say, well, when we had a k of 2x, you might say it got taller, which is true. It got taller. It became steeper, maybe. You might notice these things. You might say it's starting to look more like an exciting ski hill. Okay, you might notice that this red one might be exciting to ski down, whereas the parent function is looking a little bit more like cross country, and now this is more like alpine. But I also just want to highlight that here is where your number is showing up. This number of k is the factor that things are stretched towards the y-axis. Here's k equals 4. It's 4 times closer to the y-axis in the horizontal. So the formal language that we would use here would be the function was compressed horizontally by factor 1/2. This is 2, and then it got squeezed by factor half. Go look. It went from 4 to 2. The input went from 4 to 2. The same input that gave me an output of 2 is now half as big. Here, with it being 4 times x, it was 1/4. It was factor quarter. 4 times a quarter gave me 1. And here, this 1/2, again, flip 1/2, or divide by 1/2 is the same thing as multiplying by 2. The output was multiplied by 2 to go there. Okay? So that's a horizontal chung chung chung. Ho, we went right through break, eh? Okay, so these are the investigations you're going to do. I'm going to wrap up now. D and C, I'm going to let you do as the exercise was intended. Here we have the absolute value function. Do people know these marks, or have you seen these marks? Yeah, we're going to go on a break, but I'm going to wrap up in like 2 minutes. Have people seen these marks before? Here is the absolute value function. So the absolute value function means erase negatives. I'm only interested in positive things. So here is absolute value of x. So here is y is equal to the absolute value of x. This is the absolute value function. It's a very pretty function. What does it look like? Sorry? It bounced. It's like something bouncing without gravity, right? It's like a laser reflecting off of a mirror, or a pool ball hitting the bank and going into the corner pocket. Okay? It's straight lines that reflect. Now, what this is a set of instructions, and it means give me the absolute distance of x from 0. So if I have a -4, that's 4 away from 0, you see? This is the point -4, 4. And then, with positive values of x, it's just the line y equals x. This is the line y equals x over here. But then with negative values of x, I take them and I reflect them. Okay, so it's just like the negative, the line there is reflected up here. That's all. This is the absolute value sign. And it says remove negatives. I'm only interested in positive values. Make anything negative positive. That's what this set of instructions is. It's a nice function to investigate because it gives us more information than a line. It has a turning point like a parabola, but it's not a parabola. It's much simpler than a parabola. It's just straight lines. Okay, so that's that function. And then you're going to investigate the role of D. So you're going to be doing things like saying, well, when I subtract a number like 3, what happens? Oh, look, it moved, and it moved over there when I subtracted 3. So you're going to investigate that. And then the other thing that you're going to be looking at today is the reciprocal function. The reciprocal function, or the rational function, is y is equal to 1 over x. So you're going to sketch that here and then investigate some transformations where you're adding to outputs. So 1 over x, that would look like this. 1 divided by x. Oh, there it is there. Here is the reciprocal function. It's these two lines that come down here, woo, and then move out this way. Or here, woo, and move out that way. If I zoom in, you'll notice that it goes through the point 1, 1. There's 1, 1. And the point -1, -1. And then as x gets very small and negative, this approaches 0, but y can never be 0. And as x approaches 0 this way, it becomes very large and very negative very quickly. And as it approaches 0 in this direction, it becomes very large and very positive in that way. Okay? So that's the function y is equal to 1 over x. And you're going to do things like add 3 to it and stuff and say what happened. And you'll see, well, it just went up higher. Okay, so those are the investigations that you will complete with those functions as well. So I wish you well. Thank you for staying with me as I went 10 minutes into your break. So we will take break and then come back and then work on our investigations.